The next talk is by Jonathan Smith, who will talk to us about augmented quasi groups and hiding algebras.
Thank you. So I want to thank the organizers for the, especially for the possibility to let us participate remotely. We weren't able to get over to California because of other travel plans. So it's great to be able to do this online. Thank you. So the work I'm going to talk about here is actually a byproduct of a big project showing how quasi groups are in some sense sort of universal in algebraic combinatorics, association schemes, and strongly regular graphs. Quasi groups being quote unquote non-associative groups. So you have the multiplication like you do in groups. It's not necessarily associative, but it is cancellative, so that you have right and left divisions. And in connection with quasi groups, people like Lambeck from way back in, I think, the 50s, noticed some weird similarities between quasi groups and Heyting algebras. The divisions being quote unquote like the residuations in Heyting algebras. And this was just an analogy. And I sort of got exposed to this when I was looking at the theory of quasi groups and quasi groups and applying theory of Maltsev varieties with the Maltsev parallelogram to quasi groups. Back when I was a graduate student, my then fellow graduate student, Peter Johnston, surprised me by showing that Heyting algebras were also Maltsev varieties with a Maltsev parallelogram. So this thing had always fascinated me. And what I want to talk about now is how, as a byproduct of this more general work, we can now put quasi groups and Heyting algebras on a completely equal footing. So unifying quasi groups and Heyting algebras. And of course, how do we unify things? How do we connect different branches of mathematics? Well, that's what category theory is perfect for. So we're going to do this categorically in compact closed categories. And I'll begin by leading you up to reminding you, quote unquote, what compact closed categories are. So in particular, you're going to see a lot of tensor products. Tensor products live in symmetric monoidal categories. So symmetric monoidal category, it's a category V with a tensor product bifunctor, which we'll use with a tensor product symbol, and a unit object 1, such that the isomorphism classes of objects, of course, could be a proper class, but they sort of form a commutative monoid with a capital M, to remind us it's probably a proper class. That's quickly saying what a symmetric monoidal category is. And one technicality, we're kind of suppressing some natural isomorphisms, but here we will have LA and RA as the natural isomorphisms between one tensor A, and then on the other side, A tensor 1. So examples, the category of sets with the Cartesian product and the terminal object, the one element set, or more generally, the category of relations between sets, again, with the quote unquote tensor product being the Cartesian product of sets, and the one element set as the tensor unit. More familiar, perhaps, categories of vector spaces or finitely generated free semi-modules over a commutative unital semi-ring. So think about vector spaces over a field, or if we take the semi-ring to be the monoid of natural numbers with 0, this category then essentially captures multisets, the coefficients n counting how often an element is in the multiset. Any entropic variety, so a variety where all the operations are actually homomorphisms from the appropriate powers, tensor product, and the tensor unit is the free algebra on one generator. And any category with a co-product plus an initial object is also a symmetric monoidal category. We'll also be talking about magmas. We don't want to use the word groupoid because that has a different meaning in categories. We'll use the product denoted by nabla, and then it's a morphism in the category from A tensor A to A. And dually, a co-magma with a delta, that's a morphism going from A to A tensor A. So compact closed categories, those are symmetric monoidal categories with extra structure. We have a duality functor star going from V to V, contravariant. We have a natural transformation evaluation, and since we'll be using algebraic or diagrammatic notation, some people call this anti-Polish notation, but Anna's here with me, so I don't want to use that name. It goes from A tensor A star to the tensor unit. Dually, though, there's this co-evaluation. Everything gets flipped around. That goes from A to, from 1 rather, to A star tensor A. And we need mutually dual so-called yanking conditions to hold. If we do the 1 tensor co-EV and then EV tensor 1, that reduces to the identity on A. And similarly, well, I've done this for A star, but co-evaluation and then 1 tensor evaluation, that also reduces the identity on A star. This for each object A in V. Typical example, just to give the flavor so you get a feel for this, finite dimensional real vector spaces. Suppose those vector spaces have finite bases, X and Y. So the tensor product, of course, has the direct product of the bases as its basis. Unit object is R with the basis, the identity element. The duality functor takes A to the space A star of functionals on the vector space A. Evaluation takes, will typically use delta sub X as the functional that takes basis element X to 1 and all the other basis elements to 0. And then X prime tensor delta X goes to the Kronecker delta, which is 1 when X prime equals X and 0 otherwise. We'll be using these delta X's a little bit later on. Co-evaluations is why we need finite dimensional spaces. 1 goes to the sum over all the basis elements of the corresponding delta X tensored with X. And then you can do the math to check the yanking condition. Just a heads up about this talk. There are more details in the extended abstract in the program, and also the full details are going to be in the paper that's fully available on my website and that's referenced from the abstract. So what I would say here in this talk is don't worry too much about checking all the details. Let's focus on just pointing out where things are coming from and just sit back and enjoy the ride. So examples of compact closed categories, category of finite dimensional Hilbert spaces, think quantum mechanics here, category of finitely generated free semi-modules over a semi-ring, including the combinatorial example of multisets. One of my favorite examples is Royale's category of Conway games. This is an absolute gold mine that's out there and nobody has started to exploit it. And I think for set theorists and lots of other people, there's going to be a tremendous amount to do working with this compact closed category of Conway games. For this talk, the category of relations between sets, we'll take the tensor unit to be a 1-element set, typically denoted by 0 for the element. Tensor product is a Cartesian product. The biproduct, both coproduct and product, is the disjoint union of 2 sets. The dual A star is just the same set. Evaluation is a relation just connecting A tensor A with 0, and dually co-evaluation is a relation connecting 0 across with A tensor A. The yanking conditions are very interesting. It amounts to this be A tensor B tensor B paired up with A tensor B B being reduced to that diagonal A hat. So you're forced, when you do the relation product, to get A to be equal to B. That's the Yanking condition. And the mysterious thing here, again, that someone should look into is sort of the connection with the arguments in the Maltsev term. You know, A, B, B, P equals A, and A, B, P equals B. So that's sort of mysterious. And again, there's something to be mined here. Okay, so our two key definitions within the concept of compact closed categories are going to be augmented magmas and augmented quasi-groups. So what's an augmented magma in a compact closed category? Well, it has mu, delta, and epsilon as a structure on there. Mu is called a multiplication structure, and whereas a typical multiplication would go from A tensor A to A, the multiplication structure takes its values in A star, not in A. So there's kind of a duality kicking in here. Co-multiplication, A to A tensor A, and augmentation, epsilon from A to 1. And the condition is that this diagram commutes. That's the augmented magma condition. And what I would say here is I'll flash you a couple of examples of this diagram commuting, but don't worry about it. It's just a magic picture that makes all this good stuff happen. So let's see how group algebras of a finite group are going to be augmented magmas. Let's say over a commutative unit ring R, could be over a field, could be over integers. So we've got a finite group G in the group algebra RG, the free module generated by G. For those of you who know Hopf algebras, we're going to take the coproduct just to be the usual diagonal and epsilon just to be the usual augmentation. But remember, we've got this multiplication structure rather than a multiplication. So the augmented magma has a multiplication structure for group elements G and H that gets mapped to delta GH. So that takes X to the Kronecker delta of X and GH. In other words, 1 if X is equal to G times H and 0 otherwise. And check the augmented magma condition, and it all drops out. So remark, if the ring here is the ring of integers, then the epsilon is the usual augmentation in the integral group ring. But in general, the augmentation need not be a co-unit for the co-multiplication. So we're actually getting away from the usual Hopf algebra kind of setup. Hypermagmas in the category of relations. So consider a set with a set valued multiplication. So pair XY goes to, I'll write this as X diamond Y. In the category of relations, we take the augmentation, as we had before, X0, co-multiplication, X tensor X, so just a diagonal relation, and the multiplication relation, we're going to relate X tensor Y to Z if X, Y, Z are all in A, and then if Z is an element of the set, X tensor Y. A hypermagma happens if this set valued product is always non-empty. And the theorem says that the set A with such a set valued multiplication on it forms a hypermagma if and only if the corresponding structure that we've set up is an augmented magma in the category of relations on sets. So in other words, a set theoretic condition of non-emptiness of all of these product sets has been captured purely categorically by the augmented magma condition. In other words, magmas and hypermagmas are treated uniformly regardless of the type. We don't have to distinguish between genuine magmas or, getting sets as the values for the products here. Everything's unified very nicely. In the magma case, of course, all this stuff going on in the category of relations is actually happening down in the category of sets. So we're talking about functions between sets, just relations between sets. Okay, now I want to work towards augmented quasi groups, and this needs a little bit of carrying and braiding in these compact closed categories. This will be a little bit technical, but don't worry too much about it. Again, the details are in the abstract or in the original paper. Compact closed category, lemma is a natural isomorphism connecting morphisms from B tensor A to C with morphisms from B to C tensor A star. You might be familiar with this in linear algebra. And we want to define a couple of swaps on 3 elements. So Tor 1, 3, just leaving the middle element alone and swapping the outside. And similarly, Tor 2, 3, written up like that. So here's a definition of an augmented quasi group, the second of our main definitions. If we've got an augmented magma, we can move the multiplication structure around using that technical stuff we just looked at, the braiding we just looked at, and those natural isomorphisms. So we have a right division structure built up with rho given by these applications of that structure, and left division structure given by applying these other natural isomorphisms there. That original augmented magma with these right and left division structures is called an augmented pre-quasi group. And then an augmented quasi group is an augmented magma where both the right and left division structures are actually augmented magmas. That's the basic definition here. Let's go back to our group algebra example and see how it becomes an augmented quasi group. So remember our multiplication structure, x tensor y goes to delta xy. And then if we follow through the technique for building up the right divisions, what we get is the right division, z tensor y goes to delta of z divided by y, or z divided by y, that's zy inverse in the case of groups. So you're seeing there how the categorical tricks have done the combinatorial flipping around of the order of the elements there. And same with the left division structure. And you can check, we do get an augmented quasi group because we get augmented magmas on both of these. Basically, the associativity wasn't used at all. So the right and left divisions, even with the group, those are not associative, and everything is working nicely. So we've got an augmented quasi group coming from our group algebra. And this also works if we have a finite quasi group instead of a group initially. So in other words, quasi groups are showing up very naturally as augmented quasi groups. Okay, so now let's get towards the Heiting algebras. So we want to go to set valued products, things we'll call Marti quasi groups. So we originally had the magma with the set valued diamond. Now let's say we've got a set valued sort of a right division like thing and a left division like thing with hypermagma structures. That's a Marti quasi group if we're all x, y, z in the underlying set. Z is in x diamond y, if and only if x is in z divided by y, if and only if y is in x dividing into z. Hypergroup if the diamond is associative, and that definition goes back to Marti in 1936. It's one of the meanings, several meanings of the word hypergroup that's out there in the literature. So we're going to drop the requirement of associativity and just talk about augmented, Marti rather, quasi-groups. So the theorem says that Marti quasi-groups, the set theoretical definition, is equivalent to the category theoretical concept of having an augmented quasi-group in the relation category. And the corollary from this, so we now finally are able to relate Heiting algebras precisely with quasi-groups. Mind you, a Heiting algebra is a meet semilattice with these adjunctions connecting the multiplication with the implications, doing it in a symmetrical kind of way. And that is then going to be a Marti quasi-group or augmented quasi-group in the category of relations if we define the set valued product to be the upset of the multiplication of the product, or the right and left divisions are going to be the downsets from the implications. So that finally has brought Heiting algebras into the same fold as quasi-groups and made our precise relationship between those two structures that were always looking very, very similar.
Are there any questions or comments? Drew?
Yeah, I was just, thanks for the talk. That was really interesting. I just had a kind of a technical question. You're typing for augmented magmas. You had the multiplication goes from A tensor A to A star, and the co-multiplication was from A to A tensor A. That seemed like a surprise. So what's the technical reason that co-multiplication isn't, say, A star to A tensor A?
Yeah, remember our philosophy here is not like the philosophy in Hopf algebras, where having self-duality is a big deal. In some sense, the co-multiplication and the augmentation, those are categorical devices to capture our set theoretical content. We had the multiplication structure rather than a multiplication so that we could do those combinatorial tricks to move the elements around using the inherent structure of the compact closed category. So we were not really, with the co-product, we're not looking for something that's going to be dual to the multiplication, you know, the way we are in Hopf algebras.
Hello. Could you go back to your previous slides, please? Yeah. So it seems to me, right, that the way in which you're seeing Heiting algebras as a quasi-group is essentially capturing the restitution property of meat. Is that?
Yeah. With this construction of the you know, using the down and upsets.
Yes. So this would also be the case for arbitrary restituted lattices, right?
Should be, yeah. I mean, the main thing is just that you've got these adjunctions going on. Yeah.
Thank you.
So maybe I have a question. Going back to Drew's question, in the case of rel, you said that A star, of course, doesn't do anything, it's just A. So in that sense, we don't need the star to capture Heiting algebras, correct?
Yeah. I mean, there in rel, A star is just the same as A. The duality is trivial for rel.
Yeah. But you do need it to fit into this the setting usual quasi groups. Do you need the star?
Well, it depends which category you want to work in. you know, the usual quasi groups are just where everything collapses down into the category of set, where the relations are actually functions.
Yes, so in both settings, you don't need the star to capture a hiding algebra to capture quasi groups, correct?
Yes, yes, yes. In these cases, yeah, the star came in the sort of linear examples or the
group ring.
multi-set type examples, but it's not showing up in any real way in these set theoretical things with the category of relations.
Yeah, thank you. Also, one more question. Now that we have connected finally hiding algebras and our residual clarities in general and quasi groups, do you think there's any way to import techniques and ideas and intuition from one area to the other?
The big thing I'm very interested in is sort of a duality for general quasi groups. So that's one direction I think might be able to do something, you know, pick up, I forget, was it Esaki duality for hiding algebras?
Yeah.
Yeah, try and, I'd love to have a duality theory for combinatorial quasi groups. There's a differential geometric version of quasi groups in what's called web geometry. It's kind of a vast generalization of algebraic geometry. So that's all in a local differential geometric setting. And there, the theory of webs makes big use of Cartan's theory of differential forms. So they have a very nice duality available in that differential geometric setting. And I've always wondered about trying to get an equivalent duality that would be available in the combinatorial setting. So I think this might be one transfer that you could do to try and steal some ideas from duality for hiding algebras, make it work for quasi groups.
Thank you.
So that I think is one certainly would be very exciting direction to look at.
Thank you very much. So let's thank them again.